And we're good. Okay, so today we're gonna go over Dijkstra's algorithm, and what Dijkstra's algorithm is it's a single source shortest path algorithm. You'll usually see it abbreviated as SSSP, single source shortest path. And the goal of it is single source means like you're starting from one place, and then you want to know the shortest path from like this one place to everywhere else. So like if we run Dijkstra's algorithm from like node 1, um like the goal is to find the shortest path from like 1 to like everything else. Um so let me go ahead and draw a distance array real quick. I'll do it like over here. So 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 what we're gonna do with Dijkstra's algorithm is we're usually gonna like use it to find the shortest path between something and something else. Um Technically we have the shortest path from like 1 to 2, 1 to 3, 1 to 4, 1 to 5, and so on. But like in order to get like any of those, it's possible we have to like check a path between, right? So if we want the shortest path from like 1 to 5, we're gonna have to find these intermediary like values. So in general, like from that problem that like you guys will have to do later, it's gonna ask you like, okay, if you're starting here and you want to go to here, what's the shortest path? Well, you still have to find the shortest path from like all the intermediary values to get there. So so essentially, I think the easiest way to do this is to just go over an example to like more so show you how it works. Um, I'll widen this a little. So so what happens in Dijkstra is we have this distance array that stores all of the distances, and then for this sake we're gonna assume it's a undirected graph, meaning like it costs 7 to go from 1 to 3. It also costs 7 to go from 3 to 1. So uh what we're gonna do is Dijkstra's algorithm is a greedy algorithm, and what it essentially means is like when we get to a certain point, we want to take the smallest amount of distance that it took to get there before we start trying to go somewhere else, right? It makes complete sense when all of the edge weights are positive, but it doesn't necessarily work when it's negative. So just keep in mind that like you can only do this on a graph with positive weights, which is what they're usually gonna be. So what we're gonna do is this distance array will store the distance from 1 to any of these other places. So the distance from 1 to itself is 0. And then what we're gonna do for every other node is we haven't traversed any edges, so we're gonna set them to infinity. Generally speaking, you're gonna choose 10 to the 18th or something that isn't going to be like accessible by the edge weights. It's why like in my template I have constant long infinity equals 10 to the 18th, but I'll just write these as infinity for now. So so we're gonna start at 1, and then we're gonna try all of the edges of 1, and then if the distance that it took to get to 1 plus this edge is the fastest way to get to like this new node, then we're going to update it in our distance array, and then we're gonna push it um into our list of things to check, a priority queue, and then we're gonna update the other nodes from then on. So one important thing to notice is, like I mentioned, Dijkstra's algorithm is greedy and it's really fast. And the way it accomplishes this is it's gonna be using a priority queue. So um in order to get the shortest path faster, we're going to process the nodes that have taken the least amount of distance to get there first. And maybe it'll start making more sense once we go through the example. But what happens is I'm gonna have a queue down here of like a bunch of pairs that will represent like which node we're currently at and how long it took us to get there, and we'll use that information to update some of the other ones. So at the very beginning, oh, also just real quick, like graph notation. So the number in the circle is which node it is. So this is node 1, 2, 3, 4, 5. And then these blue numbers are the edge weights. So it costs 4 to go from 1 to 2. And then I said it was undirected, so you could also go from 2 to 1 costing 4. So So what we're gonna do is the only pre-initialized thing we have is that the distance to get to our starting point is 0. Um, so now what we're gonna do is we're gonna push into our queue. We're gonna push uh 0, comma 1. So what this notation will mean is this first number will be like the distance like to get here. So I don't know, to distance to here, and then the second number will be like what node we're actually on. So we're gonna start at our starting point, and it's gonna cost us 0 to get here. So now what we're gonna do is we're going to check all of the edges that connect one to something else, and we're going to add this edge weight onto how much distance it took us to get here, and we're gonna check if that's less than like the current best distance to get to here. So we're at 1, so we have to check all of 1's edges. So now let's try this edge right here, right? This top one. So if it currently took us 0 to get here and this is 4, that means that we can get to edge 2 in like 4 like distance or units. So since our current value stored is infinity, then 4 is better than infinity, so we should definitely update our shortest path to 2. So now to our knowledge, it costs 4 to get to 2. And now I'm going to push this into our priority queue. So it costs 4 to get to 2, and then we're done with this one. So now we move on to our next one, which is this one. So currently it took 0 to get to 1. So if we add the 7, it means that we can get to node 3 in 7 distance. Currently we have infinity. 7 is better in infinity, so we're going to go ahead and update it. So now it costs 7 to get to 3, and I'll go ahead and add this to our priority queue as well. So distance 7 at node 3. And now I'm all done with this 0, 1, so I'm going to remove it from the priority queue. And now we continue on. So as I mentioned, it's a priority queue, so we're going to pick from the smallest first number, right? So whichever node has the smallest amount to get to there, that's the one we're going to pick next, which will be this one. So now we're starting at node 2. So let's pick this edge first, right? So if it took us 4 to get here, and we can use this edge of weight 4 to get to node 1 in 8 distance, right? But our distance to node 1 is 0, so it'd make no sense to go 1, 2, and then back to 1, because it wouldn't help us. So 8 is greater than 0, so we don't update it. Now we go on to our next edge, which is this one, so we can go to node 3 on distance 2. Um, it took 4 to get to 2, so if I do another 2 here, it means we can get to 3 in distance 6. Our current best distance to get to 3 is 7, as we can see in this array. And since 6 is it's a shorter distance than 7, I'm going to update this with 6, and then I'm going to re-push it in our I'm gonna re-push it in our like potential candidates. So it would go between these. So I'll just move 7 comma 3 down, and now we push 6 comma 3. Um, next node, we have this one right here. So we can get to node 4 with distance 10. It already took us 4 to get here, so I have to add another 10. So it means we can get to node 4 in 14 distance. That's less than infinity, so I'll go ahead and update it. So now we have 14. And then uh the last node we have this one right here. So, or the last edge. So it takes 8 to go from 2 to 5, and it took 4 to get from 1 to 2. So we can get to 5, and 4 plus 8 or 12. So I'll go ahead and update these. And then I forgot to say it, but for the sake of this problem, let's find the shortest path from from 1 to 5. So by the end of this, we'll have all of that. So we're all done with this one, so I can get rid of this. And then I also forgot to add this last weight, so we can get to 5 in 12. So I'll add 12, 5. And then now we keep moving. So the next best candidate is 6 comma 3. So we have to process all the edges again, so we can go back to node 1 in 7 plus 6 distance, but 13 is more distance than our best stored, which is 0, so we wouldn't update it. Likewise with this, we could go back to 2, which would take 6 plus 2 distance, or 8, but we can already get there in 4 distance, so we're not going to update it. The next one we can pick is this edge right here, so we can get to node 4 in 6 plus 2 distance, or 8, and our current best way to get to 4 is 14, so this distance of 8 is better, so I'm going to update it. And then now I have to add it into the priority queue as a potential best, so I'll shuffle this. Control 5 down again, and then I have to add 8, 4 here, because remember, it's a priority queue, so it has to be sorted by these distances here. So the last edge to check for this one is distance 5 to 5. So it took 5 to get to 3, so it means I can get to 5 in another, or it took 6 to get to 3, and then this is 5, so it means I can get here in 6 plus 5, or 11 distance, which is better than 12. So I'll go ahead and update it. So now I'm done with this one. And then now what's our I would also have to push the 11, 5. So maybe I should have made more room for these. But so this is what we're working with now. And then now let's process the rest of these, right? So you'll notice that this node is it took 7 to get to 3. But if we look in our best distances, we know that we can already get to 3 in distance 6, right? So the cause of this, right, is the first thing we did when we started this problem is we try to go from 1 to 3, which is distance 7, right? That's what this is. This is like going from 1 to 3. But we found a better path going from 1 to 2 and then 2 to 3, which only cost us 6, right? So because this one is kind of outdated and it's not gonna help us by trying to update stuff with a worse distance than what we already have, right? What we do is we actually just ignore it. So we go ahead and move on, because if we've already updated everything that 3 connects to with a distance of 6, trying it with a distance of 7 will only give us worse results. So we go ahead and ignore this, and that'll help us from processing things that like are guaranteed to not give us better answers. So if we keep moving on, now we have distance 8 to get to 4. So we have to try all the edges for node 4. We can go to node 2 in 8 plus 10 distance. So in 18, we can go to 2. That's worse than what we have, so we're not going to update it. We can go to 3 in 8 plus 2, or 10 distance. That's worse than what we have, so we're not going to update it. And then now we can get to 5 in 8 plus 2, or 10 distance. Our current best way to get to 5 is 11, which means that this way is now faster. So I'm going to go ahead and update that. So now we've found a new way to get to 5 costing distance 10. And that should be it. And then now I have to push the 10 comma 5 in. And you'll notice, since this is the end, none of these nodes will update anything, right? And we can go ahead and try it. So if it took 10 to get to here, then we can try going to 3 and 15. That's worse, so we're not going to do that. We can go back to 4 in 12. It's worse, so we're not going to. We can go back to 2 and 18, which is worse, so we're not going to do it. So this is done. And then likewise with this one, right? Um, so this is like that whole thing of like, if the distance in here is higher than the distance that we already have, then it can't give us better results. So we go ahead and skip those. And then by now, we're all done. So if we wanted to find the distance from 1 to 5, we would just print the value at index 5. And we're done. So the takeaway from this is what you're gonna have is a priority queue full of the distance that it took you to get to that node paired with the node itself. And you're going to take the smallest value, or whichever like number in the priority queue took the smallest distance to get there. And you're first going to check is this value uh like better than the distance I have to get here? Because remember, in the case of us having this 7 comma 3, right? We had already determined that the shortest path to 3 was 6, but we have this value of 7, which is worse, right? So we're not going to process it. So in the case that this value right here is worse than the distance stored, then we ignore the value. And If it is less, meaning we can use it to update values, we process all of the edges, check to see if adding this current distance plus the edge will give us a better answer to get to this node right here. If it is, we update it and then we push it into priority queue and you just continue this process. So it's just a priority queue, a while loop, and some if statements to check if the new distance is better than the distance you have stored. Any questions? Um, you might get caught on some stuff like adjacency list storing graphs for this problem. So like I said, just focus on like calling me over if you get stuck or anything. Just make sure uh you understand the working code by the end of this. So if you guys are all good, in that case, check out the problem. I'll go ahead and stop the recording.